Right, so this lesson is about our friend Einstein. We just we all know Einstein? Yeah. It's popular in China also, and Korea. Yeah.
He has a famous picture.
Yes, right.
Now.
Yes, I know this picture. You know the picture? Yeah.
Book.
Okay, yeah. Famous picture indeed. Okay, so Einstein's equation. You got this? Yeah. Okay. So, something went wrong with that. Okay. So I think I said this before, but if I didn't, I'm saying it again. Because the mass of a photon and neutron are so small, we do not use kilograms because the mass is so small. We use a different unit. We use a smaller unit known as the atomic mass unit, or AMU. The symbol is U, or AMU. I think in the exam they usually use U. And 1 U is this much kilograms. Now, in fact, this is on your calculator, I think, somewhere. Number 17.
Wait, so the number 0, 1 and number 17 are the same?
Nearly the same. It's actually a small difference.
Isn't it just the mass?
One AMU is not quite the mass of a proton. Up until now, it didn't really matter because we were only going to 2 or 3 decimal places, but it will matter for this lesson. Can you see it's number 17? You see that? Yes? Yes? Continue? Note, the mass of 1 proton or 1 neutron is about 1 AMU. It's roughly the same as this, but not exactly the same. Alright, here is an experiment done about 100 and something years ago. Cockcroft and Walton experiment. So what they did was they had some hydrogen and they fired it. They fired the proton, the hydrogen, at the lithium plate. And when the hydrogen hit the lithium, it became 2 heliums. So, how many protons do I have here? 4. And how many here? 4. And how many nucleons do I have here? 8. And here, 8. So is this balanced? Yeah, it's balanced. So, in the experiment, it was a simple enough experiment. They had some lithium plate, and they had something that fired a proton, and the proton would hit the lithium plate, and I think it would bounce off, and it would come off as 2 heliums. Okay, so that's a simple experiment. Is it balanced? It seems to be. Now let's have a look at the masses though. So the mass of 1 proton is 1.007 AMU. The mass of the lithium is 7.016 AMU. The mass of the helium is 4.002. Okay.
temperature?
Yeah, I think this is an important one. Now, let's calculate how much mass we have to start. 1.007 plus 7.016. So on the left, the mass is 8.023 on the left. So can you write that maybe here, 8.023 U? Got that? Okay, on the right, we have 2 multiply 4.002, and you can see that we get, on the right, 8.004. So here you can write 8.004 U. So what's the problem? Have a look at those numbers. It's smaller.
Some mass is gone.
Some mass is gone. Can you see that? Where did it go? We said this is balanced, yeah?
Energy.
Yes, yes. So, yes, energy and heat. So mass does not disappear, or can it? So yes, the mass has not really disappeared, but what happened is it's, as you said, it's become energy. So, well, we'll continue anyway. Walton did not decide one day to do this experiment. He was trying to prove a formula that Einstein proved. Einstein predicted that when atoms combine in a nuclear reaction with some of their mass appearing to be lost, it was not lost. It was just changed into energy. And not only that, Einstein had a formula for how much energy you should have when you lose some mass. So Einstein said the energy you should get, delta E, should equal delta M, the mass you lose, multiplied by c squared. Or more commonly written in books is just E equals mc squared. So this is Einstein's famous formula. What's C?
Speed of light.
Mm-hmm.
Delta N is the change of mass, right?
The lost mass, yeah. And delta E will be the gained energy. Hareen?
Speed of light.
Surprising, huh? What has the speed of light to do with anything about mass and energy? Find out next year. For some of you, maybe. No, no, not you. Computer. Speed of light, yeah. The C.
Which one?
3 times 10 to the 8. Who's doing physics next year? Anybody? What are you doing exactly?
Chemical engineering.
Not Einstein.
No, don't know if you'll find out the reason why. What are you doing next year?
Geophysics.
No.
Hell.
No. No.
Oh, computer science.
I guess you'll never find out. Sorry to tell you this. And so Einstein's formula, it is surprising that the C is here because this is energy, this is mass, so why should light be important for this formula? But it is. Okay.
Should explain in 1 minute why.
1 minute why.
What was
The question is, this is energy, this is mass, so why should the speed of light be in this formula? What has speed of light got to do with energy and mass?
1 minute.
Oh my goodness, 1 minute. Simple explanation. So, okay, I'll try my best to explain. So what Einstein figured out was that you can go faster and faster, but there's a limit to how fast you can go. The most you can be is less than 3 times 10 to the 8. Speed of light. Yeah, so this is the fastest you can travel. Now, if you want to travel at this speed, then the only way you can do that is if you have no mass. That's the only way you can go this fast. Like light, it has no mass, so it can go this fast. So what happens is, when something goes faster and it's nearly at this speed, its mass actually increases and its energy increases. But you can't reach this speed because the mass keeps increasing, and if you reach this speed, your mass would be this and your energy would be this. So the only way you can make this speed is if you had no mass to start with. Then when it increases, it's still 0. So what Einstein discovered is that energy, mass and light, they all have this relationship, because the light is the maximum it can travel at, and as you get near the light, the mass increases and you need more energy. So they have this kind of relationship between the three of them.
Why is it
Good enough? Yeah.
Why is it that the faster you go, your mass increases?
But see, what's going to happen is, I'll explain it and then you'll ask another question. It's like, oh, well, why this? And it'll just keep getting more complicated. Okay?
Will you stop that?
I think so. Now, if you wanted to read more about it, you can read up about Einstein's subject called special relativity, SR. Einstein. Yeah, my goodness, I can't remember how to spell Einstein. You can read up about it, or you can watch YouTube videos about it. There's videos that explain what's happening. But it's interesting because you would never have guessed that C should be important here. It's light, you know. Okay, let's have a look at some examples.
That's why I say you're smart.
You're very smart, very smart. So here is the experiment Walton was looking at earlier. How much mass was lost? What did we say? Yeah, well, what was it on the right? 8.004, wasn't it?
Yeah.
And what was it on the left?
8.023.
Oh, 8.0023, yeah, sorry. So the difference is...
Not 00, 8.023.
Ah, right. Okay, so 8.023 minus 8.04, is it?
0.04.
So the difference is small.
Yeah.
Thank you, Sophie. 0.019. .019 U. Now U is on your calculator. What number? 17. So the lost mass is 3.155 times 10 to the minus 29 kilograms. So the energy is 2.836 times 10 to the minus 12 joules. Now, I know that this looks very small, but in fact it's very big, because the mass is 10 to the minus 29, but the energy is 10 to the minus 12. So the difference here is a lot. So it will be like saying, I guess, it would be like saying 1 kilogram of coal makes, what is coal? Oh, hang on, let's go back. Okay, wait. I know this looks very small because it's 10 to the minus 12 joules, but the mass was 10 to the minus 29 kilograms, and there's a big difference here. For example, if you had 1 kilogram of coal, you know coal, the black rock for the fire, yeah, that's like saying 1 kilogram of coal makes that many joules, 10 to the 17 joules. So if you had 1 kilogram of coal that made this many joules, that's a lot of energy, okay? So I know the number is small, but I want you to understand that it's actually a very big number for the small amount of mass you had. This is huge.
So increase the energy.
Yeah, lots of energy. This is small. Yeah, this is what you get in the formula. When 1 proton hits 1 lithium, it makes 2 heliums and that much energy. And that's a lot of energy for this, you know, it's just 1 proton. 1 proton hits 1 lithium, makes 2 heliums and a lot of energy. 10 to the minus 12 is actually a lot for the size. This is the energy here in the formula. The missing energy, this is it here. That's a lot. That is a lot. Okay. Continue. Yeah. In this example, the proton hits the lithium. In their experiment, the lithium was sitting on a lithium plate and the proton was fired at it like this.
Petroleum energy higher than coal.
Which energy?
Petroleum.
Petroleum? Petrol? I don't know what it is. It's something like, I don't know, is it like 1 litre is 1 megajoule? I don't know. Do you do it with Lorraine? It's not as much as this. It's not as much as this. This is really high. Okay. This is actually the exact mass of a proton, 1.007276. Okay? You don't need to remember these because if you need them, they'll give it to you in the exam. And also, mass of the proton is on your calculator. So that's fine. Now, the mass of a neutron is this, 1.008665. Actually, I think, if you can write these 2 numbers down, it would be good. Yeah? Yeah. Okay, you have this? So do you remember what an alpha particle is? What is inside an alpha particle? How many protons? Oh, no, you should remember this. 2 protons and 2 neutrons. This is an alpha, yeah? 2 protons and 2 neutrons. So can you calculate what the mass should be? 2 protons and 2 neutrons. What should the total be? You get it? What did you get?
6.8.
No. Do it again. Thank you. Go ahead, Amanda. 882.
Wait, but
You typed it in wrong.
it's two.
No. You typed it in wrong. 2 protons plus 2 neutrons. Yeah, 4.031882. Don't type it in my numbers. Yeah, this.
What is the difference?
Are you using AMUs?
I'm using the MP.
No, that's going to be in kilograms.
Oh, okay.
Huh? Number 2. But I don't want you to use kilograms. I want you to use AMUs, what I have on the board. So when you add them together, you get 4.031882 AMUs. Use, yeah? Okay. So when you add them together here, you go 4.031882 AMU. And what's really strange is when you actually measure the mass, it's not 4.031882, it's only 4.002602. So there's some mass missing. When you take 2 protons and 2 neutrons and put them together, the mass is not what you think it is. It's actually smaller. So there's some mass that's missing. 0.02928 AMU is missing. This is called the mass defect. So you don't have to write all of this down. I just want the idea. The idea is this. When you put the protons and the neutrons together, some of the mass then is missing. This is called the mass defect. Okay, you got that? Yeah? This is a bit strange. Think about it. It's like me saying, look, you got your 2 protons, you got your 2 neutrons, and then when you put them together, you have less mass than when they're separated. It's strange, right? I mean, why should that happen? You put them together and it's less mass. And the reason is, it's because the missing mass has become binding energy. So if you think about it like this, why would a why would a proton and electron stick together? Why do they stick together?
Because it's different poles.
Yeah, this is positive and this is negative. Why would a neutron and a proton stick together? Or even a proton and a proton? For example, this is helium. Should they stick together if this is positive and positive? Should they? No, they shouldn't. Of course they do, because that's helium. And why should a proton stick to a neutron if this is neutral and this is positive? Why should they stick together?
Because they like each other.
Well, possibly, but no. Can you see how strange this is? Why should they stick together if they're both positive? They shouldn't.
You can stick together because of the number of electrons.
Isn't that the bonds between helium?
Like
that's why
intramolecular bonds.
That's why you might have this, but that's helium with another helium. My question is, inside the helium,
Oh.
why should the protons stick together? They shouldn't really, because they're both positive, you know. So what's happening here is when you have like protons and neutrons sticking together, they stick together, they require some energy to stick together. They don't naturally stick together. Do you need any energy to put an electron with a proton? Well, no, because electron and proton, one is negative and one is positive. So what should happen if they're close together? They should want to stick together. But if you have a proton and a proton, do they want to stick together? No, so you need some energy to stick them together. And this energy comes from the missing mass. So the mass is not missing, it was changed into energy to stick them together. It's like a sticking energy. So this is called the binding energy of an atom. Is the energy required to hold the nucleus together. This energy E is equal to, hey look, it's the same formula, mc squared. Where m is the mass defect, that is the apparent loss in mass when the photons and neutrons are combined together, not and combined together. Let's just say are combined together. Yeah? Yes?
Protons and neutrons are combined.
Yes, they are combined, yeah. Do you do anything like this with Lorraine? I don't know, what are you doing at the moment? Do you know what you're doing in chemistry? Uh-huh. Well, this is your first class today, so... Have you done are you doing, what you call it, quantum yet? Chemical, okay, no. Chemical energetics? What the heck is that? There's a part at the back, let me see, that Lorraine does that is... Where is it? No, not this. Not this. Oh, Lorraine changed the book a little bit.
Because we get a new book.
Yeah, it's a bit different. Sorry.
This is the new book.
Ah.
It's not the new book. Organic
Not interested anymore. Right. And as a further note, right, if you have two protons stuck together and you want to split these two protons apart, so it's one proton and one proton. So when the two protons are together, it's called, what's this called? When you have two protons together? Come on. Helium. And then when they're separated, what have you got? hydrogen and hydrogen. So the energy you need to separate them is also equal to this. It's the same number. This is also the energy you need to separate the nucleus. You have to separate, to change your helium into two
So
hydrogen.
the E is both to form and to separate.
Yeah, yeah. And it's also the same formula. So what's great about this lesson is there is literally one formula for the whole lesson. For example, if you have helium, this is 2 protons. You separate into hydrogen, hydrogen. So it's also the energy you need to separate the nucleus, to break the nucleus. Okay, continue. Continue? Yeah. In an earlier lecture, we saw that the weak nuclear force is trying to push the nucleus. Newton's law tells us that the atom is not decaying, then a net force should be 0. So if you remember, I don't know if you remember actually, but if you had your uranium-238 and you have the alpha and the beta and the gamma coming off, the force which is pushing it out is called the weak nuclear force. But let's say there's no radiation. Let's say it's stable. Something, something just like helium or whatever. Stable. So there's no radiation. So that means the force which is pushing it out, it must be balanced with a force that's pulling it in. Because from Newton's first law, it will stay at rest if it's balanced. So the force which is pulling it in, we call it the strong nuclear force. So inside your atom, proton, neutron, and you have your electrons, there are 2 forces. There's one force which is trying to separate it, break it. This is called the weak force. But then there's another force which is trying to pull it together. And this is called the strong force. Which force do you think usually wins? The strong force usually wins. Because when you look around, most materials are stable. They're not decaying. So mostly the strong force is winning. But in some examples, the weak force wins, and then we have the radiation coming out. Yeah? So we have the strong and weak force inside the atom. We will not calculate these forces. It's too difficult for this. It's way too difficult. It's just important that you know their names. The weak force pushes out, and the strong force pulls in. Okay, is that okay? Continue? Continue? Okay, continuing. Well, this is a stupid picture. Continuing. Therefore, there's a counterbalance force called the strong force. And the strong nuclear force is a strong, attractive force which acts only in the nucleus of an atom over a very short range. It's the force that keeps the protons and neutrons together. Now, you do need the definition. Sometimes they ask you for Well, I'll tell you in a second. Okay, you got it? So in the exam, they sometimes ask you for three properties of the strong nuclear force. So the three properties are, number one, it's strong. So that's easy to remember. Number two, it's attractive, which means it pulls in. And lastly, number three, it's only inside the nucleus of an atom. And it's very short distance. Okay, continue. So, here's an example. I think it's like the one we did earlier. Yeah. So you don't need to write this down because it was the example we were looking at earlier. Remember when we had the two protons and the two neutrons and we put them together to make a helium? How much mass was missing? Did you? It was 0. Oh no, I thought that was for the Walton experiment, the other one. Remember, Amanda, you had it on your calculator. Do you still have it? Actually, you know what? No, wait, I have it on the slides. Go back. This example here, we said that 0.02928 was missing when we put the two protons and the two neutrons together. So you have proton, proton, neutron, neutron, and then you put them together, and what do you get? Helium. But I said 0.02928 is missing. This much is missing. So, you remember, it's very easy to do. We just do mass of the proton plus mass of the proton plus mass of the neutron plus mass of the neutron. You add that together and you compare it to this, and you can see that this is bigger, which means some is missing. And in the question, in the exam, they should give you the numbers too. It's also on your calculator. So they give you this mass. Let me see. So it's 2 of these, yes, plus 2 of these. It should equal this. Will it equal it? No. It will be bigger. Some mass is missing. This is how much is missing. Why is it missing? Find an energy. Yeah, so let's calculate how much energy. So I'll just type it in on my calculator, okay? 0.2928 U. Oh, sorry, this is 0. U is 17 and C is 28. So I just want to show you. I can just type it in on my calculator. See, This is the missing mass U C squared. The C?
Yeah.
C is this number, it's 28.
And you.
Is 17, I think. Can you see that here? So I just typed in that U C squared. Yeah.
Why are there 3 C's?
I don't know. We only need the first one. That U C squared. And then U and then C squared. Is number 17. Do you see that? That U C squared. So U is there and then C is there. Yeah. 28. It's C0 actually, yeah.
But why is it only, is this correct? 299,792.
No, you must have typed it in wrong again.
No.
4.3698 times 10 to the minus 12 joule. For what?
Value of C.
That's what have you got?
299.
Yeah, it is. Yep. Okay, did you get that?
That's not wrong.
You forgot the square.
Ah, okay.
Here's the second, right?
Yeah. Continue.
No. Yeah. How did you get it?
What? I just showed you on the calculator. No, the U is not square, just the C.
C.
Yeah. Okay, got that? Continue. Okay. Right, here's one I want you to try yourself just for practice, okay? This one here. I want the binding energy. But there's one small extra step I want you to do. I want it per nucleon. So for example here, this is the total. Yes? But how many nucleons do you have? 4. So the average would be this divided by 4. Okay? Say that again, yeah? This is the total for the helium. Yes? How many nucleons do you have? You have 4. 2 protons and 2 neutrons. So the average binding energy would be this number divided by 4, which would be, like about 1 point whatever. Okay? So what I want you to do for this question is oh wait, it's the same question. Is it? Helium?
Yeah.
It's the same question. Alright, so I'll continue it then. So the binding energy average per nucleon, so divide by 4 and you get 1.09 times 10 to the minus 12 joules. And the unit, what do you think it is? Well, it's joules per nucleon. Yeah, not per atom. Yeah, per nucleon. Well, the question is actually the same. All I asked you for is the binding energy per nucleon. So it's like the second part of it. And this is the answer here. I just divide by 4, that's all.
You need per nucleon.
I guess it's per nucleon, yeah. What is the binding energy per nucleon? I suppose it was per atom, yeah.
Wait, so like earlier, it's the one with the hydrogen, lithium and helium, right?
This one is about binding energy.
Yeah, and earlier there was another energy.
Oh, that was the energy released when you smash a hydrogen into a lithium.
Oh, very different.
There's 2 main problems for this lesson. It's when you combine atoms to make a new atom, or when you combine protons and neutrons to make an atom.
So in this question it's both.
What's happening here is you have your protons and neutrons, you stick them together to make a helium. Is that okay?
No way.
Okay, it's not okay. It's okay, Andy? Yeah. And Amanda? You sure? Okay. Continue?
Not yet.
Not yet. Oh goodness. Yes. Yes. Right, let me explain this graph. So what you have at the bottom is the mass number of the atom. So for example, mass number 1 is hydrogen, mass number 2, helium, and so on. What you have on the y-axis is the binding energy per nucleon. So for example, here this is a proton, this is how much energy you need. But of course that doesn't really make sense because it's just a proton. Helium, that's how much energy you need. And here the atom number is getting bigger. And what you notice is per nucleon you need more energy per nucleon. Iron has the most binding energy per nucleon, and then it starts to decrease. So I'll just try and explain what that graph means here with a picture. This is how much energy you need, like on average, between them. So what happens is when you stick more of them together, the average, it increases. So the energy here, you need more binding energy per nucleon, it increases. And this increases all the way up until you're at iron, where you have the most energy, binding energy per nucleon is the iron. And then it starts to decrease. So this means iron is the most difficult thing to separate because you need the most energy per nucleon. It also means that iron is the most difficult thing to make because you need the most energy to push it together. Okay? So this makes iron very stable. You know, the binding energy is very strong. It's difficult to separate it. Yeah. So sometimes they ask you to draw this graph, and what they really want to see on the graph is that you understand that iron is the one at the top. Here is the atomic number, and on the y-axis is binding energy per nucleon. And the unit they use in this graph is mega electron volts, but it's not important, you can use joules or whatever. For the exam, what they want to see is it goes up, most at iron, and then goes down a little bit. Here is the mass number, sorry I said atomic number, mass number. Here's the mass number, and then here is the binding energy per nucleon. Okay, so they do ask you to draw this graph roughly in the exam sometimes. So you don't need to get all this information on it, okay? It's not what you need for the exam. What you need is the shape and the fact that iron is on the top here. Sorry, this is mass number. I said atomic number. That was wrong with me. It's mass number. So, for example, here's uranium-235. And I think this is really kind of the end of it. You don't really get bigger than this. Yeah. So don't worry about all the information. You need this, this, and this, and the shape.
On the y-axis, what again? Binding energy per, what did you say?
Binding energy per nucleon. So I misspoke when I said atomic number, so I said mass number. Mega electron volts. We did this in fields.
red line. The bubble of the red line means the loose energy.
The red line?
Yeah, this space is empty, not red line.
Yeah, because you can't really, well, if you only have one proton, there is no binding energy. So you would have like 0 joules divided by 0 or divided by 1, you know, so I guess this goes to 0, but maybe not. This is how much energy you need to bind it, the binding energy. So for example, if you have 100 protons and neutrons, you need this much energy per nucleon to bind it together.
Should I write it in here?
No.
F is more than 50.
Oh yeah, this is like iron 50 something, isn't it? What's the number for iron? Do you have the table?
56?
Is it 56 maybe? I don't know. Yeah. Type in mass number of iron. Mass number of iron. Is it 50 something?
22?
That's the proton number maybe.
55.
55, so he. Okay. Irene, stop chatting to the girlfriend. I know you are. Is she not in class now?
Yes.
I see, that's worse. What class has she got? Business?
I don't know.
It's terrible.
Because we have to write FE, NI, FE, FE.
No, I don't need all this information. Just, you have too much.
FE.
FE is the most important. Okay, continue? Yeah. No. Okay, continue. Oh, please. Okay. Yes? Are you sure?
Yes.
Okay. Because that was the end. Now,
Wow.
wait, let me think. Because do we have time to do some now? Yes, you can start working on these. So if I've got battery power, I'll leave it. Let me stop the recording.